So we start with 9.5 kilojoules. What has to go on the bottom? It's always the same thing that's up here. Every 1 kilojoule is 1,000 joules. 4.184 joules is 1 lowercase calorie, and 1,000 calories is 1 kilocalorie. Remember, the kilocalorie is just the uppercase calorie because Americans don't use the metric system. They decided to just uppercase it. If it's on top, we multiply. If it's on bottom, we divide. 9.5 times 1,000 divided by 4.184 divided by 1,000. If you wanted to, you could have sat there and taken the 1,000 and 1,000 and cancel them out. 2 significant digits means we get 2.3 uppercase calories. Easy enough. I can use the equation delta H equals MCAT to correctly solve for any of the variables. 15 grams is what part of MCAT? Mass. It's removed from an oven at 135 and it cools to 25. So which one is the final temperature? 21 degrees is the final temperature. This is the initial temperature. So we will take this minus this. Will that be positive or negative? It'll be negative. So 15.0 grams every 0.46 joules per grams degrees Celsius. And this will be 21.0 minus 135 degrees Celsius for both of those. It gives us negative 114. We're going to multiply that by 0.46 times 15. It gives us negative 787. I think 3 significant digits is what we're dealing with. Negative 787 joules is the delta H. So how much energy actually left the iron? We could just say 787 joules. Notice grams and degrees Celsius are going to cancel out in each of those. Algebra. Next, it says, given the data table, I can determine the heat of formation. So, in order to do this, we do need a data table. The data table is the table in the back. Anybody got a page for that? Looks close to 27-ish. You will have to be given a data table on the test itself. 26. So here are the standard heats of formation. So if we take a look, C6H6. Oh, anybody find that one on that? Looks like we might have to go to a data table on the internet. So let's do that. So we found 49.03 kilojoules per mole here. And we have O2. What is that one? Do we need to look at the table for that one? Did you find it on there? Is it on there? Why is it not on there? Because it's an element, and right? So there's no real heat of formation if it's in its elemental form, right? We don't have to form it from the elements if it's already an element. So that's going to be 0. And I'm going to go ahead and make lines here. Oops, I want to put that line there. So that's going to be 0. How about the heat of formation for carbon dioxide in its gaseous form?
-3, -3.5.
All right, so we look at our heat of formation table. negative 393.5. And how about water in its gaseous form? Negative 241.8. Now, if you recall, the delta H is the summation. How do these go? Like this? Or the other way? Summation of the products minus the summation of the reactants. And you have to multiply it by the coefficient. So, 6 times negative 241.8 is 1450.8. We're going to add that to 12 times 393.5. It gives us 4722. And it is negative. And we're going to add all of this together. And then we're going to subtract 0 plus 2 times 49.03, which is 98.06. So, negative 4722 plus negative, oops, that's not the negative sign, negative 1415.8. That equals that. And then we're going to subtract positive 98.06 plus 0. And I'm not going to bother with plussing the 0 there. We get negative 6,700, I'm sorry, negative 6,270? 70. Since this is addition, we're going to go ahead and go out 1 decimal place, so it'll be 0.9. And that is kilojoules. Right? So if we had 4 moles of this, C6H6, what would we need to do to this? Louder? Double it, right? If we double this, we'd have to double the amount of energy. Does this make sense that this is releasing that much energy? Well, what type of reaction is this? What type of reaction? Combustion. Does it make sense that if we burn this, it gives off a lot of energy? Yeah, especially if it's reacting with 15 moles of oxygen, right? That's a lot. And plus all that oxygen, all the breaking and reforming of those bonds, like all the breakage of the bonds and the reforming of these, that's going to be 0. Good. Last one, I can determine the amount of energy needed to change a temperature and perform phase changes. So how much energy is required to take 92 grams of ice? We have ice. And we want, it's at negative 20. We want to change it to steam at 115. So what's the first thing we need to do? Change temperature or change state? It's at negative 20. So we got to get it to 0. So that is a delta H equals MC delta T. And then what? Now it's at 0 degrees Celsius. Now we got to change it from ice to what? Or solid to liquid. So that's going to be one of those conversions, right? We're going to have 92.0 grams. Every 1 gram takes so many joules or kilojoules. And then what do we need to do? So that's at 0 degrees. We need to go where? Up to 100 degrees Celsius. So what's that going to be? That's going to be a MC delta T. MC delta T. And then we're at 115. So what do we need to do? We need to change it from liquid to gas or steam. And then we need to go from 100 degrees Celsius up to 115. So there'll be one problem at least that's similar to this. This problem is the longest type of problem. So I'm going to get a nice big piece of paper. If we recall, what we're going to be doing here is, let me see if I can adjust this. What we're going to be doing here is we're starting at negative 20, right? And let's go ahead and fix this a little bit. Let's call this 0. Down here is negative 20. So we're starting down here. We're going to add heat to get it to 0. Then we're going to melt it. Then we're going to add heat to get it to 100. Then we're going to vaporize it. And then we're going to add heat to get it to 115. What is the process that occurs here? What do we call that? Fusion, melting, right? It's also freezing. This would be the freezing point at 0. What happens here? It's vaporization, or if we go in the opposite of vaporization, that is called condensation. So, does anybody have the C of ice? (2.1 joules per grams degrees Celsius. Does anybody have the C of steam? 1.7 joules per grams degrees Celsius. Does anybody have the heat of fusion of water? Every 1 gram requires how much heat? 333 joules. And the delta H of vaporization. Every 1 gram of, every one gram of ice requires 333 to melt. Every 1 gram of water requires how much to vaporize? Louder? 2260? And where can you find all of these? You should be able to find them on the back of your periodic table. You probably want to change that to grams because remember I had them on as moles there. Is it 2260? Can I get a confirmation on that? Yep. Otherwise, you'd have to memorize those. So, first things first, we've got 92.0 grams. That's M. It is ice, so that's 2.1 joules per grams degrees Celsius. And it is going from 0 minus negative 20, so that is 20 degrees Celsius. 92 times 2.1 times 20. That gives us 3,864 joules. So remember, we are going for how much energy is required to do all this. So that's phase 1. Here's phase 2. We have 92.0 grams. Every 1 gram is 333 joules. 92 times 333. That's 30,636. 3 significant digits again. That is also joules. Next step, we're going from 0 to 100. This is the easy one. This is the one we should be used to. This is step 1, 1. This is step 2, 2. This is going to be step 3, 3. This is 92 grams, 4.184. Why is it that? That's water. And we're going 100 degrees Celsius. 92 times 100. That's 38,492 or 93. 38,493 joules. Now we're going to do 4. This is an easy part because we're going to take the 92 grams and every 1 gram is 2,260 joules. 92 times 2,260. That gives us 207,920. 3 significant digits again. Now we got to do step 5. We're going to use the specific heat capacity of steam. We still have 92 grams. Every 92 grams, we have MC, 1.7 joules per every grams degrees Celsius. Where are we going up to? 115. So what's the difference between 100 and 115? That is 15 degrees Celsius. 92 times 1.7 times 15. That's 2,346 joules. Now what do we do to all of those amounts of joules? You add them. We get, add them, we get 248,259 joules. We should only have 248,000 joules, which would be 248 kilojoules. Why? 3 significant digits. You may need to check whether it asks for it in joules or kilojoules in the end there. Questions? One of the things I asked you yesterday was to make sure that you try a few of the problems for the review packet, and then that way you could ask me a specific one. So you're going to take a look at number 5 on the second page.
Wait, I need a review.
You need a review. Boosh. Total volume hydrogen gas needed to fill a Hindenburg was 2.00 times 10 to the 8th liters at 1 atmosphere and 25 degrees Celsius. How much energy was evolved when it burned? So what we need to do first is we need to find the number of moles. We have pressure, we have temperature, and we have volume. Is there any way we can get the number of moles with pressure, temperature, and volume? It's a formula we love. What is it? Double H? Pressure, temperature, and volume. And moles. It is. It's PV equals nRT. PV equals nRT. Which of those is moles? N. So we want to rearrange this equation to solve for N. We'll divide both sides by R and T. The pressure is 1.00 atmospheres. The volume is huge. 2.00. Looks like we're going for 3 significant digits here. Liters. What is, if this is 25, I don't want to use that. What do I want to use? 225 Celsius is how many Kelvin? Louder? 298 is correct. And what is my R constant for this? What R constant should we use? It's in atmospheres, guys. We should know the R constant for atmospheres. Louder? 0.0821. And remember, that's going to be atmosphere liter per mole Kelvin. Everything's going to cancel out except for what from that R constant? What do we want? We want moles. So everything except for moles is going to cancel. Man, that's a lot of moles, isn't it? That's how many moles with 3 significant digits. So that's quite a bit. So if that is our moles, and that is moles of H2, what do we do next? Well, for every 1 mole of H2, how much energy is given off? Anybody? This is the combustion of hydrogen, right? So for every 1 mole of H2, how much energy is given off? What does it say? Yeah, right? Come on, here's the amount of energy. This is the molar heat of the reaction. So if this reaction occurs, for every 1 mole of this amount of energy is given off. How do I know this is given off? Because it's negative. So we got that big number. We're going to multiply it by 286. That gives us this big, huge number. 2.3, 3 significant digits, 2.34. 1, 2, 3, 4, 5, 6, 7, 8, 9 times 10 to the 9th. That way I can save a little writing. What happens to moles of H2? Cancels. Not sure what's going on, but yeah. And that gives us kilojoules. Number 11. So how many grams of water at 35 degrees Celsius can be frozen into ice if 55 kilojoules of heat is removed? So we want to set everything up to the delta H, which is 55 kilojoules. To do that, we need to set this equal to, first, MC delta T, which is the mass that we're looking for. It's water, so what will C be? You got it? And what will T be? T needs to go from 35 to 0. So I'm just going to make all the heat positive because we're going in one direction and we want to pull all of this heat out. So versus dealing with a negative there, I'm just going to go 35 degrees Celsius. Celsius is going to cancel out there. Now that's to get the temperature. And what did we do with that first problem when we found all the separate ones? What did we do to all of them? Added them, right? The same thing is we have 55 kilojoules of energy. We want to figure out how much it will do it. So I have 1m here. But then remember, the other thing is to take the mass and then freeze it. And every mass, every 1 gram takes, what'd you say, 333, Alex? Is it 333? 333 joules, right? Right here, per gram. So we're going to take that mass and multiply it by 333 joules, and then we're going to add them together. What's going to happen to grams here and grams here? They're both going to cancel with the masses. So I've got 4.184 times 35. That's 146.44. 146.44 plus, and that's m, right, when we multiply that. So that's this times this times this, plus how much m? 333 m. We're going to set that equal to, this is 55.0 kilojoules. Are these in joules or kilojoules? Joules. So we need to multiply 55.0 times 1,000 to get that joules there, don't we? So, whenever we take this 146.44 plus 333, we get 479.44. M. Remember, we're adding them. So that means that when we add them, the M doesn't get multiplied or anything. It's just M. It's just like saying 5 apples plus 10 apples is 15 apples. So what we need to do now to solve for M is take 55,000 and do what to it? Divide it. It gives us M equals 114.7, which will round up to 115 grams. In reality, I think I might have messed up here. I think what you end up going to do is get joules per grams when you add them. And then what's going to happen when you divide this by the joules per grams? It's going to change the grams, isn't it? So I shouldn't have canceled out the grams here. I should have canceled out the joules at the end to get grams. 115 grams. Again, this is probably off because of what? It's a type of rounding error. Oh, look, they use 6.01 kilojoules per mole. So it's an older worksheet. Since we gave it to you in grams, it made it a lot easier for you guys. Because you don't have to convert that to moles. That would have been ugly. Yeah.
Where'd you get the 353? I kind of got lost around that.
It's not 353, it's 333. It's the molar heat of, or actually that's the mass heat of fusion.
Yeah.
Others? So, question. Did you have a question? Wow. Is that a hard one? Other questions? We got time for 2 more. So let's take a look at question number 10. Again, we have a reaction, and we have here the heat of that reaction. So we're going to start with the carbon monoxide. We have 56.0 grams of it. Before we can use the heat of reaction here, what do we need to do? We need to change the matter to what? Is this 3 grams to 1 gram to 2 gram to 3 gram equal that? No. This is 3 what? Moles. So I got to change this to moles. What's 12.01 plus 16? Is that 28.01? Is it? Yeah. Every 28.01 grams is 1 mole. And every how many moles for carbon monoxide? Every 3 moles is how much energy released? Again, since it is being released and we know that, we're just going to change that to positive. 56 divided by 28.01 times 24.7. How much heat is released? Oh, I need to do what? I need to multiply, divide this by what? 3. And we get 16.4. Don't forget that 3 there. That's what I did. And it's 16.46, which equals 16.5 kilojoules released. Cool. Alcohol feels cool whenever you put it on. It's absorbing the energy and evaporating off. So isopropyl alcohol is used in rubbing alcohol mixtures. Alcohol is cool. Skin cools by evaporation. How much heat is absorbed by alcohol if 10 grams evaporate? The heat of vaporization of isopropyl alcohol is 42.1 kilojoules per mole. So what you would need is the formula for isopropyl alcohol for this. Somebody want to look that up on the internet? This is the actual structure of isopropyl alcohol. This is the formula, C3H8O. So we have 10 grams of it. Again, is this in grams or is this in something else? This is in moles. So what we need to do is we need to figure out what the molar mass of that is. 12.01 times 3 plus 8.08 for the hydrogen plus 16 for the oxygen. It gives us 60.11. Every 60.11 grams is 1 mole. And every 1 mole is 42.1 kilojoules. So 10 divided by answer times 42.1. It gives us 7.00 kilojoules. All right, so on page 1, this is the ammonia combustion problem. It says when ammonia combusts, nitrogen gas and water vapor are produced. So, NH3, it says write the thermochemical. Let's do it down here. NH3 plus, and we're combusting this, so what is we combust it with? O2. Yields nitrogen gas and water vapor. What is the formula for nitrogen gas? N2, because it is diatomic, and for water vapor.
For combustion, doesn't it usually have to produce water and carbon dioxide?
Yeah, this is a combustion of nitrogen compound. So what is the water vapor? H2O. Again, both of these would be in their gas form if we were taking state of matter, gas and gas. So, is it balanced? No. First thing I see is messed up is the nitrogen. So what do we need here? 2. It gives us 3 hydrogens. 3 times 2 is 6. That gives us 3 oxygens. So 2 times what equals 3? 1.5, which means we're going to need to do what to everything here? Double it. So this will become 4. This will become 3. This will become 2. And this will become 6. Questions there? Looks good to me. So it says when ammonia combusts, this is the amount of kilojoules per mole of NH3. Well, how many moles of NH3 are combusting now? 4. So what do we need to do to the 317? Multiply it by 4. Is this endothermic or exothermic? Produced. So if the heat is being produced, then that means it's what? Exo. So that means that delta H is negative. Right? So little things here. So we take a look. It says how many grams of ammonia need to be combusted in order to generate 1.75 times 10 to the 4th joules of heat. So we start with what they give us. This is joules. My answer here is in what? Kilojoules. So I need to change this to kilojoules. Every 1,000 joule is 1 kilojoule. Every, what goes on bottom of the next step? Every 1,268 kilojoules of energy required 4 moles of ammonia. And every 1 mole of ammonia weighs what? 17.04 grams. So 1.7 times 10 to the 4th. Actually, it's 1.75, huh? 1.75 times 10 to the 4th. Divided by 1,000. Times 4. Divided by 1,268. Times 17.04. We get 0.941 grams. All right, so here we've got number 5. Some ice at 0 degrees Celsius was placed in 244 milliliters of water at 28 degrees Celsius. What is the mass of 244 milliliters of water? 244 grams of water, because the density is 1. All of the ice melted, and the final temperature of the water was 26 degrees Celsius. How many grams of ice melted? So what we can do is we can calculate the amount of energy that the 244 grams of water lost. And we can set that equal to the ice melting. Every 1 gram of water requires how much, or gram of ice, I should say, requires how much energy to melt? Louder? 333 what? Joules? If you don't know that, you have to have that memorized or written on the back of your periodic table. I think on the back of your periodic table it's in moles. And we're not only melting this, we're also taking it from 0 degrees up to what? 26. So that's a MC delta T. So we're going to add M, which is, we don't know. C of water is what? 4.184 joules per grams degrees Celsius. And what's the temperature change from 0 to 26? Actually, it's the final temperature is 26 degrees Celsius, so right? 6 degrees Celsius. So the amount of energy that did all of this to this mass of ice is equal to the amount of energy that 244 grams of water lost to go from 28 degrees Celsius to 26 degrees Celsius. Yeah? Final temperature of everything is 26. So this would be 26 minus 28 degrees Celsius, which would be what? -2. Remember, we can take the negative of one of these. So, -244 grams times 4.184 times -2 is 2,039.84 joules again, because that's what this is in. And that means that over here, we've got some stuff to do. We've got 333 M plus 4.184 times 26 plus 108.78 M. What can we do when we have this many M's and this many M's? We can add them. Plus 333 M gives us 441.78 M. We're going to set that equal to 2,039.84. What do we do to both sides? Divide by 4,401.78. Cancels that out. We're going to take 2039.84 divided by that answer. And we get 4.62 grams of ice. All right, so this one is in kilocalories. I will give you ones that are all in kilojoules, I believe. I can't imagine doing this. So here's the reaction that we want. Right? We have, do we have C2H6 on the reactant side? No. But we do have it on the product side, so we need to flip it. Do we have 2 moles? So we need to what? Double it. She knows, huh? So when we flip it, what happens to the sign? It changes from positive to negative or negative to positive. And we need to multiply this by 2 since we doubled it. So 32.7 becomes 65.4 kilocalories. Nothing changes just because it's kilocalories. We can add kilocalories to kilocalories. So if we take a look, we don't want to mess with oxygens because oxygens are what? Everywhere. How about CO2? You find one CO2 to mess with? Which equation is it in? A, B, or C? A. Is it 4 CO2s on the product side? It's 2 CO2s on the product side, so what do we need to do? Double it. 2, 6, 4, and 4. So that means we need to do what to the negative 337? Times it by 2. That's going to give us negative 674.4. Next thing, we have H2Os. Take a look. I've got 6 H2Os. Currently, I have how many H2Os on the product side? 4. The only other place where H2Os are right here is 4 plus 1 equal to 6. So what do I need to do to this bottom one? Double it. Another thing that I could have looked at was the oxygens here. 6 plus a half. Well, that's not equal to what? That's not equal to 7. So 2, 1, and 2. So what does that mean? 68.3 becomes doubled, right?
Why do you give us equations? Because you're not able to have half the oxygen molecule. So why do you give us equations?
So now what do we do to all these? Keep in mind, I like to cross this one out so I don't get confused. That's this one down here now. Again, if we don't flip it, the signs change what? They don't change. So all we got to do now is add every single one of those together. And we get negative 75. I'm sorry, 745.6. What are the units here? Kilocalories. Could we switch that to joules if we or kilojoules if we wanted to? Yeah. But no need. We'll do another one of these. 12 on page 3. It says calculate delta H for the following reaction given the following information. Negative 595 kilojoules is the answer. So let's take a look here. Magnesium. Do I have magnesium on the reactant side? Yes. It's not 2, so what do I need to do? I need to double this. So we have 2, 2, and 2. That means I need to do what with 641? Can Niles do that? Niles do that in his head? He can. He's so good at that. If there was like a math calculation thing, like for student of the month, probably be right up there. So there we have negative 1282. Again, I'm going to get rid of this so I don't get confused. I get confused easily, so crossing that out does a big help for me because it makes me look like, oh yeah, that's right. Is there a silicon tetrachloride on the reactant side? No, it is on the product side. So what do we need to do to this whole thing? We need to flip it. So silicon tetrachloride yields silicon plus 2Cl2. What do we need to do to this thing then? We just change the what? Sign. That's all. Now remember, I got rid of this one because I flipped it. What's going to happen to the Cl2s? They're going to cancel because they're on opposite sides. If they're on the same side like the oxygen last one, they add up. So we have CiCl4, we have 2Mg, and then we have 2MgCl2, and then we have Si. So what do I need to do to these two things? Right, I need to take negative 1282 and add to it positive 687, and we get negative 595. What are the units here? Kilojoules, because they were given in kilojoules instead of kilocalories this time. So let's finish up with another Hess's law, right? Calculate the delta H for this right here. So we're looking for CLF. CLF only located in one place? Right here, but we have 2 moles here and we only have 1 mole here. So what do we need to do to this one? We need to half it, right? So we get 1/2 there, 1/2 there, 1/2 there, and 1/2 there. So 167.4 divided by 2 gives us 83.7. Right? Next thing is F2. Do you see any F2s anywhere? Yeah, we have F2 here. That's the only place, right? We have 2 moles, so what do we need to do? We need to half it. Negative 43.4 divided by 2 is 21.7, negative 21.7. And CLF. Do we have CLF as a product anywhere? The middle one, but is CLF a product? No. What do we need to do with that one? Flip it and half it. Cl2O plus 1 and 1/2 F2O yields ClF3 plus O2. So we flipped it, so 341 becomes negative, and 341.4 divided by 2 equals 178.7. I'm sorry, 170.7. What do we do to the rest of these? Well, we could go through and say, okay, so I have 102 here, and I have a half and a half here, so that's going to cancel. I've got ClF3 here, that's good. I have 1 and 1/2 FTO. Here is 1 FTO, and here is 1/2 FTO, so that's going to cancel. I have a half of Cl2O. So I have a half here, and I have a half here. So that's going to be fine. All I need to do is add up all these, and it should be good, right? Remember, this negative sign does go with this, so I'm going to redo it. I'm going to put equals in that. Negative. Actually, we need to cross this out so I don't get confused. Otherwise, I'm going to get confused. Negative 170. Negative 170.7 plus negative 21.7 plus 83.7. And that gives us 108.7. And it is negative. Units again are kilojoules because these are kilojoules. So the delta H of this reaction is negative 108.7. Page number 4, number 1. This is very similar to the lab that you did. You took lithium let's get it on there. Lithium hydroxide, and you put it with water. So what we need to do is we need to find the change in heat of the water. So delta H equals MC delta T because the temperature changed. What is the mass of the water? Nope. 112. What's the specific heat capacity of water? 4.184 joules per grams degrees Celsius. What is the temperature change? Is that 11.7 now? What's going to happen degrees Celsius and grams? They're going to cancel. So 112 times 4.184 times 11.7. We get 5,482.7 joules. So again, usually when we have delta H, it's in kilojoules per mole, right? So we want to do just like we did in the laboratory. I tried to stress this a lot. We're going to start with that many joules, and we're going to put it over 6.48 grams of lithium hydroxide. What do you want to convert first? What's the easy one? Louder? Joules. Every 1,000 joules is 1 kilojoule. Next, we need to put the grams over 1 mole. What is lithium up there? 6.94? For lithium, what's the molar mass for lithium? You can't read that? 6.94? 6.94 plus 16 plus 1.01. That gives us 23.95 grams per mole. So we're going to take that times 5,482.7 divided by 6.48 divided by 1,000. And we get 20.26, 3 significant digits. So that is 20.3 kilojoules. Now here's the deal. What happened to the temperature here? Did it go up or down? Okay, so which one is greater? 25 or 36.7? 36.7 is greater. So if it went from 25 to 36.7, did the temperature of the water go up or down? Went up. So when we actually put that in there, what does that mean? It's endothermic or exothermic? Exo. So that means that this delta H is going to be negative 20.3 kilojoules because it gave off energy. So number 4 on page 1. So we have the metal, MC delta T, and we're going to set that equal to the water, MC delta T. Now, since I know that I'm not solving for final temperature, I'm just going to make these equal to each other and negate the negative of the one that basically cools down, right? Because we know that that would be negative, because this would be negative, this equal to this, and one of them would cool down and it would equal out. So I can just make them equal to each other because we're not solving for final temperature. This one's the metal for me. So what is the mass of the metal? 19.5 grams. We are looking for C, so we don't know that. And we have 99 going to 26.2. So if you wanted to do this, we would take 26.2 minus 99. That's going to equal what? Negative 72.8. And then we have the negative in front of here. So what's going to happen to this whole thing? It becomes positive. So that is 1419.6 C, being the specific heat capacity of the metal. Here's something we should know. 125 milliliters is how many grams of water? 125, because the density of water is 1. So 125 grams of water. And what is the specific heat capacity of water? 4.184 joules per grams degrees Celsius. And the difference here is 2.2 degrees Celsius. So we're going to set this whole thing equal to 125 times 4.184 times 2.2. We get 1150.6. We're going to take that whole thing and we're going to divide it by 19.6. And we get C equals 0.8105. 3 significant digits is 0.811. Everything cancels except for joules per grams degrees Celsius. Questions there? The question was about the negative here. If something loses energy, something else has to gain it. So one loses, one gains. All right, number 2 is a very similar problem. So if we take a look, we have aluminum, we have MC delta T, and we have water. We have MC delta T. Again, one side's going to be negative. We're going to take the aluminum, which is 25.0 grams. We're going to place it in, it has oh, wow. Look at that. So it's kind of a tricky problem. I'm going to go ahead and change this from 24.03 joules per degree Celsius mole. I'm going to change it over here off to the side to per gram. That's a tricky problem. I don't know why they did this, why they went moles here and grams here, but that's an easy fix. We've got 24.03 joules per degree Celsius mole, and every 1 mole of aluminum is equal to how much? 26.98 grams. What's going to happen to mole? Cancel, and we're going to end up with what else on the bottom now? We're going to end up joules per degree Celsius. Yeah. I won't do that to you on the test. I'll do worse. What? Yeah, so it's going to be 0.891 joules per grams degrees Celsius. What is the temperature change for that? From 82.4 down to 24.9. It's 24.9. The final temperature minus the 82.4 is negative 57.5. What's that going to do to this side of the equation? It's going to make everything now what? Positive, right? We want to break that off there. We want the mass of the water. We know that water is 4.184 joules per grams degrees Celsius, and we want the change in temperature. The initial temperature of the water is 22.3, so the final is 24.9. 24.9 minus 22.3, that's 2.6 degrees Celsius. So now it's just a game. Negative 25 times 0.891 times negative 57.5. And that's going to be 1280.8. 1280.8. Grams will cancel out. Degrees Celsius will cancel out. Will equal joules. And then if we take a look here, we're going to take 4.184 times 2.6. That's going to be 10.88. 10.88. What's going to happen to degrees Celsius? We're going to get joules per gram, M. Right? So if we want to find M, what do? We divide both sides by 10.88 joules per gram. So 1280.8 divided by the answer. We get 117.7. 3 significant digits gives us 118. What happens to joules here? We end up with 1 over gram. What's the inverse of 1 over gram? Gram. All right, so milliliters of water is equal to what? Grams. So we have MC delta T equals MC delta T. One is negative because one is going to lose energy and the other one is going to gain energy. So we know the C's here are both for water, so they're going to cancel out. We're going to end up with negative M times delta T equals M times delta T. The mass of the water over here, I'm just going to pick this one, is 30. So negative 30 grams times. The final temperature is what? What we're looking for? T of F minus the initial temperature is 280 Kelvin. Now Kelvin or degrees Celsius doesn't matter here because it's going to be, the difference is, as long as we keep it the same, it's going to be the same. It's fine. So if we take a look over here, we've got 50 milliliters, which is 50 grams of water. Boom. And we're going to multiply that by the final temperature minus the initial temperature, which is 330 Kelvin. Questions so far? Now, what do we call this distribution? Negative 30 grams TF minus 30 times 280. That is 8,400. And that is set equal to 50 grams TF minus 50 times 330. That is 16,500. Now what do we do to both sides? Well, I want to isolate TF. My mind wants to make it the positive side. So what is, if I add 30 to each side, that's going to be 80 grams of TF. And then I have negative 8,400 here. What am I going to do? I'm going to add this to that side. What is 1650 minus, I'm sorry, is it 16,500? 16,500 minus, it's 16,500. Minus 8,400. And that gives us 8,100. So if we take a look here, 8,100 divided by 80 gives us 101.25. Okay, let's see here. So I added to this side, right? The side here, negative 30 times the T of F, negative 30, this makes it plus. So instead of 8,100 here, we should have, thank you guys, 8,400 plus 16,500. Boom, that's 24,900. There's our mistake, 24,900. That equals the 80, so what are we going to do? Divide that by the 80, and there we get 311. Good call. So a simple redistribution of this negative 30 times T of F, negative 30 times negative 280. That'll mess you up. It caught me today. 311 Kelvin. So on B here, we need to have this heat of formation. This is on page 3. We need a standard heat of formation table. There's NH3 gas. This is page 26 in your packet for question page 313. Negative 46.2. Nitrogen and hydrogen are both what? 0. 2 times 0 and 3 times 0 is 0. So we're going to take 0 minus the summation of 2 times negative 46.2. And what is that? 92.4?
Yep.
Hey, this guy can math. Negative, since this is negative, it's going to be negative 92.4. We take 0 minus negative 92.4. We get 92.4 kilojoules. Again, this top one, this would be 0. This is CO2 gas, so that would be negative 393.5. This is H2O liquid, so that would be negative 285.8. This one right here, C2H6. Unfortunately, I don't have that, so I'm going to look that up on the internet. So what was it? 84.68. Again, this is a summation of the products minus the summation of the reactants. Forgot my watch today. So for the reactants, we're going to take 2 times negative 84.68. That's going to be negative 169.36. We're going to add it to 0. So we're going to minus that whole thing. Negative 169.36 minus 0. Over here, we have 4 times CO2. 4 times negative 393.5. That's negative 1574. We're going to add that to 6 times H2O. 6 times negative 285.8. That is negative 1714.8. So we're going to add that to negative 1574. And then we're going to subtract negative minus negative 169.36. All that's going to equal negative 3,119.44 kilojoules per mole. Right? So we need to find the final temperature, so that means we have delta H equals MC delta T. 17.1, what is that? We want the final temperature if this many moles of water at this much heat is added. So what is 17.1? Starting temperature. So we actually want T of F minus 17.1 degrees Celsius. What is the C of water? 4.184 joules per grams degrees Celsius. We know the mass here or not yet? We don't know the mass here. So we need to sit there and find the mass. 2.25 moles. Every 1 mole is how many grams? 2.25 times 18.02. If you don't know where I got that at, look at the periodic table. 40.545 grams. So that's 40.545 grams. We're going to set that equal to the amount of heat, which is 1910 joules. Well, I need to take this times this and multiply it by both of these things, don't I? Since heat is being removed, what would I do to that? This amount of heat is being removed or taken away, so that needs to be what? Negative. So 40.545 times 4.184. That equals 169.6. TF. And then we're going to multiply that by 17.1. So that is 2,900. 2,901. Apparently. Then what we'll do is we'll take and add this to both sides. Plus negative 1910. It gives us 990.8 equals 169.6 T of F. How do we solve for T of F there? We divide by 169.6. We get 5.84. T of F equals 5.84 degrees Celsius. That's the final temperature if we remove that energy, which makes sense. If we were at 17 and we remove this energy, the temperature should go down.